What is negative 2 times negative 3? In elementary school, we learned that a negative times negative is positive, so answer comes out to 6. Have you ever wondered why? Let's start by looking at some interesting examples of explanation you may get from your school teachers. Imagine a car moving backwards in time. Then, once we play the video backwards, it looks as if the car is moving forward. And we can think of this as two negatives canceling out to become a positive. Another explanation that I really like involves complex numbers. In a typical pre-calculus class, we learned the geometric intuition behind the multiplication of complex numbers. And we may think of it as multiplying the sizes and adding the angles together. So, multiplying a negative real number essentially rotates the original number by 180 degrees. These two explanations are cool, but I can't help but to feel that these explanations are trying to prove something by either providing examples or looking outside in without fundamentally justifying why it is the case. And I want to approach it from a more mathematical perspective. So, let's ask the question one more time. What is negative 2 times negative 3? And the answer is, it can be whatever you want. As long as the rules you choose to play with, which at least has to be logically consistent, leads to such conclusions. For example, the framework of arithmetic that the pre-Renaissance mathematicians agreed upon was that it doesn't make sense to multiply negative numbers, just like how we can't divide by 0. However, we don't have to play by those rules, and there is a very real sense that we can actually divide by 0. This example was just to illustrate a point, but we're going too far off on a tangent here, so a number system where division by 0 is actually allowed will be covered in a future video. It is true that breaking rules in mathematics is very fun, and it often leads to new discoveries. But that really isn't the intention for this video, and I want to introduce a framework where negative times negative actually comes out to positive. And that framework that I am about to introduce, mathematicians call them a ring. Let's start by defining what a ring is. A ring is a set R equipped with two binary operations, addition and multiplication. And what exactly is a binary operation? Take any two elements A and B in the set R, then A plus B is in the set R, and A times B is in the set R. And sometimes we call this the closure property of addition and multiplication. And in the context of ring theory, we often skip the multiplication symbol. And there are several additional properties, and let's introduce one at a time. Both for addition and multiplication, it has to satisfy associativity, meaning pick any A, B, and C in R, then A plus B plus C is equal to A plus B plus C. And this irrelevance of the order of operation allows us to remove parentheses. And similar holds for multiplication as well. And to see the power of the associativity of an operation, we can take a look at an example of a non-associative operation and realize how much we have taken associativity for granted. And the next property that we want is the identity for both addition and multiplication. And what does it mean? There exists a special element called the additive identity, which is often called the zero element, such that no matter what A you pick in R, A plus 0 or 0 plus A is equal to A. And similarly, there exists a special element, the multiplicative identity, which is also called unity, or sometimes just called the identity, which gives us a feeling that mathematicians privilege one operation over another. The next property is the inverse property of addition, which means take any A in the ring, then there exists a corresponding element, additive inverse of A, often called the negative of A, such that if you add A with its inverse, it gives you the additive identity. And having the negative allows us to define a new operation called subtraction, which is first element plus negative of the second. Notice how the inverse property is not required for multiplication, But in case the inverse property does hold for multiplication, we say the ring is a division ring. The next property is the commutativity of addition, which means take any a and b in R, then a plus b is equal to b plus a. And in case the commutativity does hold for multiplication as well, then we say that the ring is a commutative ring. And finally, there is one last property called the distributive property, which holds for both operations. Which means take any a, b, and c in R, the left multiplication splits over the addition, and similar holds for the right multiplication. And this concludes the definition of a ring. And notice how all of these properties are something we learn in elementary school. And at the moment, this definition seems a bit too abstract, so let's take a look at some motivating non-examples of a ring. Consider the set of all positive odd integers, with addition and multiplication defined the usual way. What is 1 plus 3? Well, in this universe of numbers, 1 plus 3 is not defined, so addition fails to be a binary operation, and thus this set is not a ring. Then how about the set of all positive integers? Can we find an element in the set such that 2 plus x is equal to 2? And such x does not exist in the set, so this set fails the zero property and thus is not a ring. Then, how about the set of all non-negative integers? The set does contain the additive identity. Now, can we find x such that 3 plus x is equal to 0? And there is no such x, which tells us that 3 does not have an additive inverse, which tells us that this is not a ring either. Then, how about the set of all integers? I'll leave it to you as an exercise, but this set indeed satisfies all of the ring axioms. In short, we can intuitively think of ring as a set where we can add, subtract, and multiply any two elements, but not necessarily able to divide. And looking at Ed Sheeran's first 4 albums, it is pretty clear that he did not study ring theory. And if we look back at the definition of the ring, and multiplication is missing commutativity, can we think of any example of a non-commutative ring? The set of all 2x2 real matrices form a ring, and the multiplication is non-commutative. And to see this in action without calculation, each 2x2 matrix corresponds to a two-dimensional linear transformation, and we can see that rotating 90 degrees counterclockwise first, then stretching vertically by a factor of 2, yields a different result than doing it in reverse order. So, in this generalized framework called ring theory, where we have a set and two operations with some familiar properties, we are ready to prove that negative times negative is positive. Soon, we will see that this result follows naturally from just these properties. And any result that we prove will hold not only for familiar number systems with usual notion of addition and multiplication, but whatever set that satisfies ring axioms, such as the set of 2x2 matrices. The first theorem that we are going to prove is that the additive inverse of any element A is equal to A itself. By the definition of additive inverse, A plus negative A is equal to the additive identity, the zero. And similarly, negative A plus its additive inverse is also equal to 0. So, if we look at A plus negative A plus negative of A, the left two terms add to 0, so we get negative of A. And similarly, the right two terms add to 0, so we get A. And this shows that taking inverse twice gives you the original element. The next theorem says that take any two elements A and B in the ring, and let C be A plus B, then A is equal to C minus B. And the proof starts by adding negative B on both sides, and B plus negative B comes out to 0, So A is equal to C plus negative B, which by definition is C minus B. And this formally justifies being able to move a term to the other side of the equality. The next theorem says take any A in the ring, then A times 0 is equal to 0. And we will start the proof with 0 plus 0 is equal to 0. Then we can multiply by A on both sides and use the distributive property. And using the theorem 2, we can subtract A times 0 on both sides. And by the definition of inverse, A times 0 plus the negative of A times 0 is equal to 0. And this shows that 0 times anything is equal to 0. The next theorem says take any A and B in the ring, then A times negative B is equal to the negative of A times B. And we'll start the proof by using the previous theorem, and since we know that negative B plus B is equal to 0, we will substitute it on the left side of the equality. Then we can use the distributive property and subtract AB on both sides, using the theorem 2. And there is a slight variant of this theorem, which allows us to pull the negative sign out of the first multiplicand. And the proof is essentially the same. And this theorem formally justifies being able to pull negative signs out of products to the front. And the last theorem says that take any A and B in the ring, then negative A times negative B is equal to A times B. And the proof starts by applying the previous theorem 2 times and pulling out the negative sign twice. And by theorem 1, negative of negative is equal to the original element itself. And this concludes the proof of what we have set out to solve. And we use nothing but the very definition of what a ring is. So, in the framework of ring theory, we can conclude that negative 2 times negative 3 is equal to 2 times 3. But what we have done is much stronger, and the theorems that we have shown holds for any set that can be classified as a ring. How do we solve this equation? Over the integers, or real numbers or complex numbers, we have the zero product property. So x minus a is equal to 0, or x minus b is equal to 0. However, there is a number system that we are all very familiar with, such that the zero product property fails. Hint: take a look at a clock.